We left off here looking at a spring oscillating, or mass oscillating at the end of a spring. Um, just a quick recap, notice here is the rest position or the equilibrium position. So right here and right here, the mass is at its equilibrium position. Now, we started off pulling the spring outward, stretching it. So notice the object's not moving, its velocity is 0, but there's a restoring force, that F equals minus kx thing. So we're at position x, the force is in the negative direction from that. We pulled it positive direction, the force is pointing in the negative direction. So that's Hooke's law. So now that force is going to, we release, the force is going to accelerate the mass. So now the velocity will be not 0 from here to there. It's accelerating. By the time we reach here, the force has dropped from a big magnitude down to 0. But the velocity has built up quite a large velocity. So while it's right here at the rest position, it would love to stay there, but there's no force acting on it. But it's moving, and object in motion stays in motion, so it overshoots and goes through, compressing the spring. So now it's over here. There's a restoring force pushing it back. And so there's an acceleration that's slowing it down, or a deceleration, and it stops right here at negative x. Okay, they use a for amplitude there, where the x position is. So notice it comes to a velocity of 0 at the same distance on the other side. But now there's the maximum force there, in fact, equal to the other one, because F still equals negative kx. So now the force is going to push it back, and the same discussion applies. We're here with no force, but a big velocity, and so it pushes through. So notice you have the greatest force when the object is stopped at the extreme far ends. And you have the largest velocity where the force is 0 in the middle. Okay? And you can see how it's following a sine pattern here, a sine wave, where A is the amplitude of the sine wave. So wave theory is going to evolve out of this quite naturally. So they walk through that a little bit, what we just did. It's moved to position A, which is their maximum x value, and there's a maximum force there. Okay? When it accelerates into the middle where position is 0, no force, but it's still moving and it keeps going and so on. So we talked about what's on this slide already and what's on this slide, because now it's being decelerated back to 0, and then the restoring force pushes it back again. Notice the time for one complete oscillation from here to in and back out again, that's exactly one period. So the period of oscillation is going to relate to, obviously, the force involved here. Okay? But we'll see that in a little bit. Now, notice also that not much is going to come out of this discussion here, but I should mention also, and I keep going back, we'd like to handle this algebraically, but it's not possible to do because the force is changing constantly. Maximum force here, but as you move in, the force is constantly decreasing to 0. Remember, F equals ma, that worked fine for constant forces. But if force is varying, we had to go back to the integral, do some calculus, right? And that's what's happening here. The velocity, so we got velocity, delta x over delta t, except the velocity is constantly changing. The acceleration is constantly changing as the force does. And so since all these values are changing, the equations relating force, velocity, acceleration, position, relating all those things to each other, we need to use calculus to get those. Okay? If we get far enough through here, I don't know if we're going to have enough time in the air, I'll real quickly show some of you that are in calculus how to derive the relationships. It's fairly straightforward as long as you know your derivatives of your trig functions, which I think you guys have done in calculus by now. But that's a future you problem. Now, notice again, this we're not going to do much with, but if you take from the amplitude to the rest position, that's 1/4 of the period. Then from the rest position back to the negative amplitude, that's another 1/4. From there back to rest is a fourth, and from there back where you started is another fourth. So again, going back to the picture, from here to the rest position, that's 1/4 of the way through the period. From rest position to the other end, that's another fourth of the period. From that end back to rest position, that's another fourth, and from there back to where we started is the last fourth. So again, we're not going to do anything with that other than noticing that's kind of interesting. You add up all those little pieces and you get the total. Of course, you can break it down into an infinitely small number of pieces and get the integral again for you calculus survivors. Now, they do this, I don't know, if you would actually attach a pen to that mass and have it draw on the table beneath it or whatever as it's oscillating, maybe have a scrolling tablecloth underneath it or some such, you would see that it traces out a sine wave as it starts. Now here they're starting compressed rather than stretched, but whatever. It's compressed, it pushes out, it stretches, it pulls back, it's compressed, and so on. And if you let it map that out, it maps out a perfect sine wave. The amplitude of the sine wave is simply the value of A, that x value that we stretched or compressed the spring. The period is the time to go from one peak to the next, or one trough to the next, or whatever, to complete one cycle. So this simple harmonic motion, oscillatory motion in general, is going to be governed by sine waves and cosine waves. Okay, so remember, just remember that we're going to come back to that. For now, though, and I'm going to leave this alone for now. For now, what I want to do is look at how the force relates to the period. The spring itself has a force constant K, remember. F equals minus Kx. That K is the constant for the spring, right? So, if the spring has a very small constant, which means it's a very loose spring, the kind of spring you might find inside your pen, where it's easy to force it and press it, compress it, and stretch it, and so on, you're not going to get much force produced there. So it's going to take a long time to accelerate up and get pushed back and forth, so you're going to have a long period. On the other hand, if you have a very stiff spring, a spring that you'd have a hard time compressing with your hands, you need a lot of force to do much with it, it's going to provide a lot more force, and so it's going to oscillate more quickly. So notice that the period is going to increase with K or decrease with smaller k. Now, turns out it's not an actual direct proportion. That would imply linear. If you double K, you double the period, and that's not what happens. It actually varies with the square root. Okay? But they vary in the same direction. The bigger the K value, the bigger the period is going to be. Or I'm sorry, the smaller the period is going to be. It's going to oscillate more rapidly. Okay? I said that backwards. Bigger K, the smaller the period. But again, it's not a numerical one-to-one relationship. It's a square root relationship. Now, similarly, if you have more mass, if the mass that you hung on the spring is a bigger mass, it's going to not accelerate as much, and so it's going to have a longer period. So bigger mass means bigger period. Smaller mass means smaller period. Force constant is the other way. Bigger constant means smaller period. Okay? So, putting it all together, notice that the period of oscillation is going to depend on the mass and the reciprocal of the constant. But also, as I kind of mentioned earlier, it's not just directly, it's a square root relationship. And you get actually this as your equation. Notice the relationship 2 pi here, which is going to correspond to the 2 pi that you know about from trigonometry when you did that in, I guess, pre-calculus. The period of oscillation equals 2 pi times the square root of m over k, where m is the mass you hang from the spring and k is the force constant. Mass is in kilograms, force constant is in newtons per meter. And if you plug them in proper SI units, I won't show it and go through it here, but everything cancels out and you're left with units of seconds, which is a proper unit for period. Okay, so the period of a spring, you take a mass, hang it on the end of a spring, and let it vibrate. The period is going to equal 2 pi times the square root of m over k. So plug in your mass, plug in the force constant, you can get the period. So again, if you're in space and you want to measure the mass of an object, on Earth we measure the mass by measuring its weight. We put it on an object, see how far it pushes it down by gravity, and then just the mass is related to that. In space, it has no weight. So you put the object on the end of a spring of known K. So you plug in the known K, you measure the period, plug that in, solve for the mass. And we can see if our astronauts are losing too much mass if they're in the space station for too long. Okay, so here's a sample problem. We got a 0.22 kilogram cart that's attached to a spring. The constant is 12 newtons per meter. Stretch it, release it. What's the oscillation period going to be? Well, period is 2 pi times the mass of 0.22 over the K of 12, square root it. So divide them, square root, multiply by 2 pi. I'm going to trust their math here because I'm too lazy to grab a calculator. You get 0.85 seconds. So it's going to take a little less than 1 second for that spring to push the cart, pull it back, and the one complete period. All right, so that's that. I'll give you some practice problems to do with this, and tomorrow I think I want to go on to look at pendulums then. Then after we look at pendulums, maybe we'll stop, we'll take a quiz, and talk about wave theory from there. All right, and that will do it for today.